Welcome back to our object-oriented programming series. In the previous lecture, we learned how objects are created, initialized and destroyed, and how their life cycles are managed in memory using the constructors and destructors. Now let's take the next big step. How do objects actually interact with each other and with functions? After all, in any real-world program, objects do not exist in isolation. They constantly send and receive data. So in this session, we will explore how the objects can be passed to functions, returned from the functions, and what happens under the hood when this occurs. We will also see how constructors play a role in these interactions, especially when passing by value and passing by reference. Before we move into how objects are passed and returned from the functions, let's quickly understand how real-world C++ programs are organized. Up till now, we have written everything in a single .cpp file. That is the file with the class, the functions, and the main function all in one place. That works fine for small programs, but once your project grows, this approach becomes messy and hard to maintain. In practice, we separate our program into multiple files based on their roles. So let's look at the structure. The header file with usually the .h extension declares the class and its members. So think of it as a blueprint. Secondly, the source file, the file with extension .cpp, contains the actual code that defines what those member functions do. And finally, the main program, your main.cpp file, includes the header file, uses the class, and for example by creating objects or calling methods. So this modular approach helps us with encapsulation, in which you keep the implementation details hidden. It also helps with the compilation speed, as only the changed files are to be recompiled. And this approach also exists in teamwork, as multiple developers can work on different modules independently. Let's look at a small example to make this concrete. Here the box class is split into three files: the box.h file, box.h file, box.cpp file, and main.cpp file. In box.h file, we declare what the class looks like with its data members and its functions, but we haven't defined yet how those functions work. Then in box.cpp, we actually define the member functions using the scope resolution operator, and this keeps the logic separate from the structure. And finally, in main.cpp, we include our header file with #include box.h line. Compiler now knows what a box is and can safely create an object and call its methods. This kind of organization is very essential once we start working with multiple classes that maybe interact with each other, which is exactly we will be doing when we will explore functions interactions with objects in the next session. Look at the first file, box.h. The first two lines are special mechanisms called header guards. The #if and def block. So these prevent the compiler from including this header multiple times by mistake. For example, if a file is included twice indirectly through another header, so these guards ensure that it is processed only once. And finally, the #endif tag is to end this header guard. The header file only tells the compiler what exists, that there is a class called box and it has a certain functions, but the actual function code lives in box.cpp. When we compile, the linker connects all these pieces together. And finally, in main.cpp, we just included box.h. We just include box.h. So the compiler now knows what a box is and can call its functions. Now that we understand how multi-file organization works and what these header guards do, I'm going to give you a practical example of a class or Dyn array class that we have already seen, but this time it is implemented through multiple files. So we will see how splitting it keeps the code cleaner and more maintainable, especially when the code grows. We start with the header guard, dynArray.h. Notice the first line pragma once. So pragma once is also like if and def, but this is a modern and simpler replacement for that old style include guards, if and def and define. But both serve the same purpose. They prevent the file from being concluded more than once by mistake. But pragma once, as I've already told you, that it is a more cleaner and it is supported by most modern computers. In the header file, we only declare the structure of our class, the member variables, the function prototypes. We do not write the actual logic here. Think of it as a blueprint or outline that other files can refer to. Next, we move to dynArray.cpp. This is where we actually implement the functions, the constructors, destructors, and the member functions. And finally, in main.cpp, we included dynArray.h, and then we create an object named ARR. When this line runs, the constructor from dynArray.cpp automatically executes, allocating memory and displaying a message dynArray created. Now that we have seen how to structure our code into separate files, let's move on to the next important concept: how objects interact with functions. Specifically, we will see how to pass objects to function and return them, and how constructors and copy constructors come into play. Let's see what happens when we pass an object by value to a function. Here we have a simple class box with one data member length, a constructor and a destructor. Constructor prints a message when it is called, and a destructor prints another message when the object is destroyed. So this helps us see when copies are created and destroyed. In main function, we create an object b1 with length of 10, and the constructor runs once, and we will see the message constructor called. Next, we call the function display and pass b1 to it, but since the parameter is passed by value, C++ creates a copy of object b1 and sends that copy to a function. Inside the function, when we modify by writing b.setLength function, then we are changing the copy, not the original one. After the function ends, the copied object goes out of scope, so its destructor runs and frees that temporary memory. Then when we return to main function and print the length again, we see that b1 still has its original length of 10. So all the changes and modifications are made to the copy, not to the original one. So notice how two constructors and two destructors are called, one pair for the main object and one for the temporary copy. So this behavior can cause unnecessary overhead when working with large objects. So to solve this problem, we often pass the objects by reference instead of by value. So let's modify the code and see how the changes both the behavior and the performance. Now we pass the object using a reference. Notice that ampersand sign in the parameter list. This means b inside the function is just another name for the same object in main. So no copy is made. So only one constructor and one destructor run. When we change the value to 20 inside the function, it updates now the original object. So back in main function, the change is now visible immediately as no copy is made and all the modifications are made to the original object. So now let's move on to a more interesting example that explains and demonstrates how objects can interact through functions. We will explore multiple ways to add distances using one object as a receiver and other as an argument. So this will help to understand how data flows between the objects depending on which one calls the method, the member function. In the first case, we have three objects, dist1, dist2 and dist3. The goal is to store the sum of dist2 and dist3 inside dist1. Now notice how the call looks like. That is dist1.add_dist, and you are passing dist2 and dist3 as argument. So this will use dist1 as a receiver object, and this will pass dist2 and dist3 as an argument to the member function. Now inside the function we take the feet and inches of d2 and d3, we add them and assign the result to the calling object, that is dist1. Here you can see that dist1 was updated. It received the sum of both the other objects. So whenever we call a member function using the dot operator, the object on the left side of the dot becomes the current object, that is the one on which the function is operating. This is very important. So inside the member function, whenever we refer to a member variable directly without using a dot or object name, it automatically refers to the data of this current object. In case 2, now let's see what happens when the object calling itself is one of the operands. Now let's see what happens when the calling object itself is one of the operands. For example, d2 dot add the underscore dist, and the arguments we will be passing d2 and d3. So this time the receiver and the one argument refers to the same object in the memory, that is d2. Here is the key observation. Since d2 is both in the caller and one of the arguments, the function first makes a copy of d2, but the actual updates happen on the calling object through this. So when the function adds d2 and d3, it ends up adding d2 to itself, effectively doubling its value. Now let's talk about static data members. Normally every object of the class has its own copy of member variables, but sometimes we want one common variable that is shared among all the future objects. For example, to count how many objects have been created. So suppose we have a class, say employee, and we want to keep track of how many employees have been created. We might be tempted to add a regular integer variable called maybe count inside the class, but here's the issue. When we create multiple objects, each one gets its own copy of that count variable. That means for example, I have multiple objects created for the employee class, E1, E2 and E3. That means E1 has one count, E2 has another, and E3 has its own. So they do not share a common value. So if I try to increment count in one object, the other objects do not get updated because they have their separate versions or copies of that object. So the total count will always stay incorrect. Each copy only knows its own version. So to fix this problem, we might think of using an external variable outside the class, like sort of global variable, but then we can lose encapsulation as the data no longer controlled by the class itself. Alternatively, we can create an initialization function or an update function that keeps the track manually. But that would mean remembering to call it every time the object is created, and this is also an error-prone approach. What we really need is a variable that's the part of the class, but it is shared among all its objects, something that exists only once, no matter how many objects of the class you create. That's exactly where static data members serve the purpose. To do this, we use the keyword static when declaring the variable inside the class. A static member belongs to the class itself, not to a specific object, so it is class level. Static member variable belongs to the class as a whole, not to any one object. Every object can access it, and when one changes it, the change is reflected for all the objects. So next we will look how to declare a static data member, define it properly outside the class, and see how multiple objects share the same value automatically. Let's look at how to declare a static data member. So when we create 3 employees, E1, E2 and E3, there is only one copy of count shared by all of them. Every time we call the member function setData, it increments the same shared counter. Notice how we define the static member outside the class using that scope resolution operator. So this step is mandatory. It allocates the storage for that variable. So you write a data type int, then a class name employee, then scope resolution operator, then the name of a variable, that is count in this case, and then you initialize also at that place. So when we display the data, even though the count is used by each object, all three show the same cumulative value, proving that the count is shared. In addition to static data members, we can also have static member functions. These functions operate at the class level again rather than the object level. So static functions are declared with the keyword static, and they can be called directly using the class name. So we do not need to create any object. So here show count is a static function. It accesses the shared variable named box count, which keeps track of how many objects of box have been created. So static members and static functions are a great way to manage the data and behavior that should be common across all the instances of the class. Now here's an important rule about static member functions. They can only access static variables of the class. Let's see why. This is because the static function doesn't belong to any specific object, it belongs to the class itself. Since it is not called through an object, it doesn't have access to instance variables. So there is no this pointer available. We will see this pointer in a moment. So inside a static function, we can only use other static members, not the regular data members of our individual objects. This is another example of race car class, and we aim to add or have a cumulative count of how many cars have been added in the game of race cars maybe. So we need to define a static variable for counting the number of cars. We named it num of cars, and for demonstration we have added another variable that is non-static, that is not static, named. So this is a regular data member, not a static one. So now let's look at a static function. So as I already explained the rule, so static functions can only access the static members. So when we write cout num of cars, it doesn't show an error. When I try to write or access score variable, so since static function can only access static members, so this will throw an error. Then then you can also see the function below, that is non-static. So this is a regular member function, non-static function. So in this you can access both the non-static and static data members. So the rules applies only on static member functions. Next, let's talk about constant member functions. This is a very small and a brief but important concept in C++. A constant member function guarantees that it will never modify any of the object's data members. In other words, it promises not to change the internal state of the object. Now let's see why do we need that? Well, in large programs, especially when working with complex data, we often create functions whose only purpose is to retrieve the information, not to modify it. For example, functions like get name, get balance, or show data, these functions just read and display the data. These are perfect candidates to be declared as a constant function. So by making them constant, we are telling the compiler and the programmers that this function is safe to call even on constant objects, and that will not alter any data. So let's look at a quick example. So you can see in an example, the first function is not constant, but the second function is made a constant member function. So our data member is named as alpha. So in the first function we can easily update the value of alpha as 99, and nothing stopped us and there is no error. But in the second function, you can see the function is declared as constant member function. So here when we try to modify the value of alpha to and set it to 99, this will report an error. that you cannot modify a member. So this is how constant member functions work. Now that we understand how constant member functions work, let's see where they really becomes useful when we declare entire object as a constant. So when an object is declared as constant, it means data members cannot be modified at all after initialization. In other words, you are telling the compiler this object state should never change, and that has an important consequence. Since you cannot modify a constant object, you can only call functions that also guarantee not to modify it. So this is an important rule, that you cannot modify constant objects, so you can only call functions that also guarantee this rule and make sure that you do not modify any of the data member. So that's exactly what constant member functions do. So only constant member functions can be called on constant objects because they are the only ones that promise not to alter or modify any data. So here obj is an constant object, and that means we cannot change its data. So calling set value would cause the compiler error because it tries to modify the object, but calling get value is fine since it is declared as constant and it only reads the data. No writes have been made to the data members. So it only reads data and no writes are being made. So this combination, the constant objects with constant member functions, helps to ensure data safety and enforces a clear separation between reading and modifying operations. So now let's look at another important concept in C++ classes, that is this pointer. Whenever we call a member function for an object, C++ automatically passes a hidden pointer to that object into the function. That hidden pointer is called this. So inside any member function, this pointer always points to the object that invoked that function. Let's look at this simple example. Here we have a class named where, and inside it a function named reveal prints the value of this pointer. So in main function we create an object w and prints its address using $w. So when we called w.reveal, it prints the address stored in this. Now when you run this program, you will notice something very interesting, that is both addresses printed are exactly the same. That's because inside the reveal function, this is literally pointing to the same memory location as the object w in the main function. So we can say that inside any member function, this is a pointer to the current object, that is the one that call the function. So this pointer is extremely useful when we want to refer explicitly to the current object, to its current instance. And now that we know that what this pointer is, that is a pointer that refers to the current object, let's see how we can actually use it to access objects' contents. Remember, this is a pointer, and pointers do not hold values directly. They hold addresses of memory locations. So if we want to access the data members of the object that this is pointing to, we first need to dereference it just like any other pointer. That is done using a static operator. So when we write static this, we are saying go to the object that this pointer refers to. Let's see that in code. Here inside the reveal function we are printing static this dot v. That means take the object pointed to by this pointer, then access its member v. Now even though v here is uninitialized in this example, the focus is on understanding the mechanism. So this gives the address of current object and static this refers to the object itself. So inside the function, static this dot v means v that belongs to the object that called this function. We have already learned that this pointer refers to the current object, and by dereferencing it we can access the object's data. Now let's take it one step further and see that there are other two equivalent ways to access a member variable through this. So inside the reveal function we are printing the same member variable v in two different ways. The first statement uses static this dot v, which means take the object pointed to by this, then access its member v. And this second statement uses this and again this sign, which is just a shorter and cleaner way of writing the same thing. So these both are equivalent ways, both access the same data member of the current object. Now in practice, most programmers prefer using the arrow notation because it is easier to read and avoid extra parentheses. But conceptually it is good to remember that under the hood both forms the same thing. So when you see arrow operation member name, think of it as a convenient shorthand for static this dot member name. So both are valid and both rely on the fact that this is a pointer to the current object. Sometimes we use parameter names in our functions that are the same as our class data members. When that happens, the local parameter hides the member variable, and this is called naming collision. To resolve this, we use this pointer to clearly refer to the class member. For example, if both the member and parameter are named value, we write arrow operator value is equals to value. So the one on the left refers to the data member and the one on the right is a parameter. So this makes the code unambiguous and ensures that we are updating the object's actual data member. Now let's look at another powerful use of this pointer, the cascading function calls, also called method chaining. Sometimes we want to call multiple member functions on the same object in a single line, like obj.setx5.setxy and maybe many other calls in a single line. So this style makes the code shorter, cleaner, and you can say more expressive. To make that possible, our functions must return the current object itself, and that is exactly what this pointer allows us to do. So in this example, set x and set y both return static this, which refers to the current object, that allows us to chain the next function call right after the previous one. When we write p dot set x 5, so the first call set x returns the object itself, which then calls set y, and finally the show function. So this technique is widely used in modern C++, especially in the stream operations and fluent APIs to make the code more expressive and readable. Here's another example that demonstrates how cascading function call work, but this time using this pointer directly. So in this program we have a class called demo with 3 member functions, fun1, fun2 and fun3. Each of these functions print a message and then returns a pointer to the current object. Now look at the main function. When we create an object named ob and then call ob.fun1, then arrow operator, then fun2, then arrow operator and then fun3. So let's break down this statement and see how it executes step by step. First, ob.fun1 is called, and inside fun1 we print fun1 called and then return this, which is the pointer to the same object ob. Now the return pointer this immediately calls the next function in the chain, that is fun2. So inside fun2 again a message is printed, fun2 called, and the same this pointer is returned, still pointing to ob. Finally, using that return pointer we call fun3, which prints fun3 called. In the previous example we saw how cascading function calls work when each function returns a pointer, specifically this pointer. Now let's look at a variation of an idea where each function returns the object itself, not the pointer. Here in the class demo we have 3 functions, again fun1, fun2, fun3. Each function prints a message to indicate that it is being called and then returns static this. So now this time it means it returns the current object by value. Notice the return type of each function, and this time it is demo, not demo static. It means each call produces a copy of object rather than returning a pointer. When we call ob.fun1, the following happens step by step. So the first step is fun1 is called on OB object. Secondly, the message fun1 called is displayed. And finally, fun1 returns a copy of this object, that is a temporary object created from static this. Then on that temporary object, fun2 is called. Again, message is printed and it returns another copy, another temporary object. And finally, fun3 is called on that second temporary object, and then we see our relevant print message, that is fun3 called. So we can use this pointer to avoid naming collisions. As in the function, you can see that if we write r is equals to r, then this is ambiguous statement. So we can use this pointer to avoid naming collisions, like this arrow operator is equals to r or static this dot r is equals to r. Now that we have seen how this pointer can make our member functions more powerful, now let's move to another very practical concept, that is array of objects and array of pointers to objects. In real world programs, we often need to manage multiple objects of the same class, like handling a group of students, multiple bank accounts, or a list of customers. Just as we use arrays to store primitive data types, we can also create array of objects. Here you can see that our three student objects, S and S of 0, S of 1 and S of 2, are stored sequentially in memory. Each object occupies its own block of memory and all the three blocks are adjacent to each other. Since we declared them as a normal array, the memory allocation happens automatically on the stack. So when the program exits main, all the three objects are automatically destroyed in the reverse order. Now let's look at the difference between static and dynamic arrays. So in a static array such as student S of 3, that is we created three objects on the stack, one after another in contiguous memory. The compiler automatically allocates and deallocates this memory, so when the function ends, all the three objects are destroyed automatically, as we have just seen in example. So in contrast to this scenario, when we create a dynamic array, for example using new keyword, new student of 3, so this array is now created on the heap. The variable s itself lives on the stack, but it points to the first element of a heap allocated array. So this approach is flexible, as we can decide the array size at the runtime, but it also means we must manually release this memory using delete keyword. Otherwise we will end up with a memory leak. So in short, static arrays are simple and managed automatically, while dynamic arrays are flexible but they require manual memory management. Another way to access the elements of dynamic array, instead of using the traditional subscript notation like p of 5 for example, you can use a pointer notation and pointer arithmetic. So pointer p points to the first object in the block. Using the arrow operator p and that arrow operator, we can directly call the member functions or the set data function for that object. For example, p and that arrow operator, and then we can write a function set role. After that, we use p++ to move the pointer forward to the next object in the array. Now let's see a slightly different concept, array of pointers to objects. So unlike normal array of objects, this array doesn't directly store the objects themselves. Instead, it stores the addresses of objects that are created separately, usually on the heap. So in this code, we declare student static s of 3. This creates an array of basically 3 pointer variables, each capable of holding address of a student object. Inside the loop, we use new keyword to create each object dynamically. For example, as I is equals to new student. So all 3 objects live in different parts of the heap memory, while the array itself lives on the stack and holds the addresses. So the array itself is stored on the stack and it only contains 3 pointer variables. Each pointer stores the address of a student object created dynamically on the heap. So the objects themselves student object 1 2 3 live at different heap addresses. When we call s of I and that arrow operator show role, for example, we are using arrow operator to access the object that si points to. Finally, since the objects were created dynamically, we must manage the memory and we must destroy them using delete keyword. Otherwise, the memory will remain occupied. So that's it. Thanks for watching. In the next session, we will see how objects are copied, what actually happens when we assign one object to another, and how we define our own versions of operators to make object interaction more intuitive. Let's continue this journey to mastering object-oriented programming with C++ with the next lecture on copy semantics and operator overloading.